Hi, good afternoon. My name is Jonathan Velasco, and I work as an application specialist here at CSC. I focus on electromagnetics, and today's webinar will be focused on Elmer FEM and its applications in electromagnetics, particularly in the case of electrical machines. Induction machine models are analyzed by comparing experimental results against commercial FEA software and open source software Elmer FEM. And computational time is compared and studied between Elmer and other commercial options for a different number of cores. So our presenter is Mr. Zair, who was born in Kanewal, Pakistan in 1988. He received his bachelor's degree in engineering from GIK Institute of Science and Technology in 2011. Then he went ahead and obtained a master's degree in computational engineering from Lappeenranta University in Finland in 2016. And he's currently enrolled as a PhD candidate in electrical engineering at the same school, Lappeenranta University of Technology, where his main interest is in the modeling of and simulation of 2D and 3D electric drives. So here, Mikael, if you can explain the audience the guidelines for the webinar. Thank you.
Hello to everyone, old and new. And so here again, I'm Mikael from CSC also, and a part of the background team organizing this webinar series. So to repeat from last time's a few practicalities again, we have a Q&A window. As the last time, we ask you to pose your questions to the presenter in the Q&A window. This webinar is also recorded and will be viewable within a week. I'll post the web address to the playlist for the webinars in the chat window shortly. Also, I'll post a link to the materials of previous webinars, and that's the same place where the material for this one will be posted as well. If you want a speaking turn, please raise your hand. We will address all questions at the latest after the presentation, and also delegate speaking turns after the presentation. Minaj, please.
Yeah. Hello, I am Minhaj Zahid from LUT, as my colleague has introduced me, and they have introduced me quite well. So today I will be talking about some of the practical applicabilities of Elmer FEA in the field of electromagnetics, and especially in the converter-fed induction machine analysis. So the main point of this presentation is that the Elmer FEM computations, they are analyzed and they are compared with the measurements. We have laboratory setup here to compare, and then the commercial FEA is also used. The commercial FEA name is Altair Flux, so which is also used to compute some results. So yeah. And continue to the next slide. I will show you some of the outline of my presentation, and today I will talk about something about the open source softwares, and what is the motivation and why Elmer is I have chosen, and then I will introduce you the machine model and some of the results from the experiments and from the commercial and FEM, commercial and Elmer software, and then the future work which we are planning to do. Yeah. So first about the open source software, that open source software are particularly transparent. Transparency is the main feature of open source software, and then secondly, they are license free. You don't have to pay anything. Now nowadays, like commercial software, they are heavily charged by the companies and the providers. So this is the one of the main usage. So some platforms enables flexible modification of modeling features, like some of the open software, and it is also possible to include attributes that do not exist in commercial software. For example, the open software platform support alternative for pre-processing and post-processing. So you can choose your software which you are proficient in, and then you can play with it. So some of the open source software, well-known software like FEMM, GetDP, SME, Lib, and Plican. They are some. These are some open source software which I find like, but they have some limitations, and some of the parameters they are limiting those open source software, and still they are doing some development to carry on the work. And why Elmer? So Elmer is also an open source software. So the reason why I choose is that it is also a multi-physical computational tool, and it is very efficiently using message passing interface technique, and for the parallel computation. And the one more good thing about this Elmer is that it is using I can use the external resource like CSC supercomputers to run my heavy simulations, so which are time taking. So the last one is like research and development of this software is very fast, and they are collaborating with universities and industry to make it more efficient. Like our university is also collaborator of CSC and to develop the Elmer. So practical applications of Elmer, if I talk about some practical application, so Elmer is particularly used 17% in electromagnetics, and solid mechanics 20%, and the main thing which is fluid mechanics. So 26% of people they are using it to solve the Elmer platform to fluid mechanics things, and 29% is used for heat transfer calculations. The now moving towards the pre-processing and post-processing, like some of the for the like Elmer are using 3 steps we can use. So first one is pre-processing, then we have to import this geometry to Elmer grid for environment, and then after that some by using some commands we use to Elmer solver is used to do all the things. So 2D meshes and 3D mesh structure they can build in various softwares, some like ANSYS, Abacus, FI, DAP, COMSOL, Gmesh, SolidWorks, and people mostly use Gmesh, Solme, and Antigen, NetGen for creating and meshing structures. To run the model in Elmer FEA, the mesh is first converted, as I told you earlier, that it is converted to Elmer mesh, and then sent to the Elmer grid environment for the processing. So the last step is post processing. Post processing can be done in Paraview, MATLAB, or Python, whichever software suits you. So Elmer post processing people are using like 40% of people they are using Paraview to see the all the things like electromagnetic stuff like flux densities, current densities, impact on Fourier loss calculation, and these type of stuff. So people are using 41% people are using Paraview, and Gmesh, like for the modeling, Gmesh are using people are using 3% of people are using Gmesh, and the Elmer post people also use Elmer post to calculate all the things. So the next thing that I will introduce about my machine. This is the rough sketch of my model, and it is taken from ABB's slide shares, and my colleague Alex Antila, he has used it in this machine also in analyzing some of its behavior. So it is basically a squirrel gauge induction machine having squirrel gauge and stator at the top. So this machine is 5 kilowatt, and there it is basically used in research here at LUT, and in collaboration with ABB. So this machine is also very much used in variable speed applications such as power conveyor belts, robots, electrical vehicles, cranes, elevator, and other home appliances. So this machine is very much applicable in the industrial and home usage point of view. So this is my model which I draw in Gmesh. So Gmesh Gmesh was used to draw this structure, and this structure consists of basically the model was having 48 stated slots and 40 rotor bars. So due to some symmetric issues, so I have used just 12 bars and 10 rotor bars to model this machine. And this Elmer simulation you can see on the second right is also done by Powell, so which he was working over here in this university. So he has also computed some things, and I particularly carried his research to the next. So the main finder was Powell, but after that I continued that work. And this slide shows like 2.5T model of my machine, and the distance between the slices is 0.04, and the motor has 8.5 degrees skew along the rotor bar, and number of slices there are 4. And it is done some of the previous research, like it already showed that 4 to 6 slices we can have some good results and fast results. So the link of this is also mentioned, the research link is also mentioned over there. And the next slide is telling us about some of the comparison between commercial and Elmer FEM parameters. Like as you can see that commercial and open source software both are using Maxwell equations to calculate the electromagnetics, and Bertozzi model for the loss calculation, and both are using MPIs. And the core limit which commercial software, because it is used at the local computer is used, so the limit of that was six cores, and open source can use 520 cores, and even more can be used. So it depends on which script like you are running for. Are you running the long job or some other jobs? Like, so everyone has its own core, but in my case, like what I researched, it's like it can use the 520 cores. And external resources, obviously commercial software cannot use the external resources, but as I told earlier, that open source software has some extra advantage that I can use CSC supercomputers to run my simulations. And let's talk about some of the results. So this on the right, like the figure is showing about current versus time. So the green one is measured waveform, which was measured in our lab, and it is showing the peak current of 15 ampere. And the second is blue one. Blue one is the from the Elmer source, Elmer FEA, and the commercial FEA is showing the red one. So, but this is using 2.5T. This graph is for 2.5T, and commercial is 2D. And on the right of my screen is the torque comparison between the two machines. So the torque is also matching with the commercial, and almost same spikes are observed, even though the Elmer computation are transient for transient simulations, and the commercial simulations they were at coupled load simulations. So even though they are showing the almost exact match, and the accuracy is almost same. So the next thing I will talk about the loss analysis. So as I told you earlier, that commercial software and the Elmer software both are using, and both have used Bertozzi model, advanced Bertozzi model to solve the iron losses. So the iron loss comparison for if I see 400 volt and 50 hertz, they both are flux and Lipotti measurements. They are almost showing the same thing, and Elmer showed a little bit higher results. So, but it is still acceptable. The error percentage is less than 2%. And as I move to lower frequencies, the commercial FEA showed little bit less losses, and but the Elmer FEA, it showed like quite much near to the measured results. So, and on the right, like I'm comparing the total electrical losses with respect to frequencies. So blue line is for open source, and black line is commercial. And the measured results, they are actually they are a bit higher, because here, like stray losses and stray losses, friction losses, and these are not considered. So the blue line and black line, they are just for electrical losses for FE, and that's why they are little bit less and little bit low. So from these two lines, like black lines and blue lines, we can see that the loss calculations, they are very much close to each other. So Elmer is particularly showing the things which are close to the commercial FEA. So we cannot like distinguish that much between the two softwares. And the source is also shown over here, that my it is in from my research publication. And my supervisor Pia Lind, he has computed the commercial software results. So Pia Lind and Lassi Arningori, they are my supervisor, and they have computed the commercial one. And the next thing I want to show you about, to tell about the laboratory measurement compared with the Elmer FEM. And it is like when we consider the stray losses and additional losses in the machine. So these losses, they are actually analytically calculated from the Elmer FE results. So power and current, they were basically used to calculate all the things. So while comparing these two results, if we see the overall total losses, the measured loss was total losses was around 570, and the calculated the post processing losses from the Elmer and analytical point of calculations, they were 564, and they were actually quite much in contact with each other. So the accuracy is not that bad, but uh, still we need to do something to accurately see the additional losses and stray losses and friction losses in the machine, so we can find something which we can do it in Elmer also. So these results are taken from my publication, which is in review in the ACED conference. And the next thing I will talk about, I will compare the 2D results and multi-slice results with the measured results. So if we see that the total losses which are in the measured data, it is 510, and for 2.5D it is much closer and much relevant to the much closer to the measured result than as compared to 2D. And they are basically comparing the electrical losses. So as I told you that that stray losses and friction losses and mechanical losses, they are analytically calculated, so by from the equations. So I didn't consider these things, so I just compared the electrical losses which are computed during the post processing. So they show that 2.5D is showing like much good results and much higher current value, stator current value, which is required, and good iron loss prediction is given from the 2.5D point of view. So it takes some for the, if I talk about the computational time, then computational time of 2D and 2.5D is not that much different. So I forgot to put one slide over here about this time comparison of 2D and 2.5D, but they were almost like taking not the same time, but like 2 to 3 hours in difference, like. And for the, if I talk about this Elmer and commercial FEA computational time, so in this slide, like I have compared the two things, like I used the motor boundary condition and conforming boundary conditions in my geometry. And the motor and boundary condition and conforming boundary condition, they were studied at two different time steps, like. And first was like 16,000 intervals, like time intervals, and second is 16,000 intervals. So the time size was changed in both the things. And the relation between the computational time to the number of cores is obviously it is observed that it is not linear, and computational time decreased more than 50% when increasing the number of cores from 14 to 26 for the 16,000 intervals. And conforming boundary condition, on the other hand, it requires some less computational time, because conforming boundary condition, they usually lessen the number of nodes in the computation, so less computation is required, and the time is decreased when the number of cores are low. But as we increase the number of cores, the difference is very small. Very small. And the details about this conforming and motor boundary condition, it is already mentioned in the Elmer manual, and the one who want, he can go through it, and actually it is a very good study, and it should be considered. And when we compare the Elmer and commercial time, so computational time, we see that the commercial FEA time size was we put was 0.8 seconds for the both, and the number of nodes, they were also same for the both. Calculation time step is also same, and the core limit, as I told you earlier, that the commercial is done on local system, so it is using the 6 cores, and open source I used 6 cores, the same cores, to compare the time. And the computational time which found from the commercial software was 33 hours, and from the open source software, which I calculate, is also around 33, like 32.5 or 32, something like this. So it was around 33. So the computational time was matching, but the plus is that in open source FEM, we can use more cores and more parallelization technique to reduce the computational time and get the result faster. But on the other hand, commercial software is bound to our system, so we cannot use more limits and more cores. So these results are basically from my publication, and it is also mentioned in reference is also given in the previous slide. The local system, as I told, that it is bound to the system. So the system was having Intel Xenon W2135 processor, which is 3.7 gigahertz, and 6 core was used, and NVIDIA Quadro of P2000, and it was 5 GB 5 GB RAM is used in this system. So the results are quite much comparable, but as I told earlier, that it has open source have some good thing, the advantage that we can increase the number of cores to get the faster results. And these results, they were in my research, they was actually from Taito supercomputers, using the Taito supercomputers. So it is obsolete now. Nowadays Pohuti server is active, and you cannot use the Taito anymore. So, and if I so the next research which we did for Elmer FEA is that we have some measured results from PWM supply for, laboratory experiment. From the laboratory experiment, in the laboratory experiment, like 1 microsecond was used, and Elmer, if used this time step, it will take too much long time to compute the results. So what we did, we downsampled this time to 10 and 50 and 100 microsecond to check what time step is giving the accurate results in Elmer FEA. And the simulation was transient simulations, and the sinusoidal supply was supplied to start the motor first, and then in Elmer we changed the supply from sinusoidal to PWM. After it reached to steady state. So this can be done in Elmer by two ways. What I could see is two different ways can be used to done these things. Like if you want to start a motor with sinusoidal supply and just want to switch after this reach to steady state to PWM supply, we can do it in two ways. Like first way is to write a script like for or which is for the U phase, W phase, and V phase in .f90 file, and then you can call this file in the circuit body in the zip file. And the other way is like because I have the measured data my voltage in the numeric form, so I use the .dat file. I put all the things in .dat file from the measured results, and then fed this data to Elmer to compute the to see that the both the supply are in synchronizing, and all the things which are used in measured setup, it is applied to the Elmer FEM. So the good thing is that it is very easy in Elmer, and we see that the results from our study is quite much okay. And the transient simulation actually it takes several supply periods to reach to the steady state, therefore reducing the simulation time for induction machine is very important issue, and while using the higher mesh density. So as I told earlier that 1 microsecond it was reduced to 10 microsecond and 50 microsecond and 100 microsecond to check which one is giving the accurate results in my research. So the Elmer FEM result showed that 1 microsecond were too time consuming, but the THD percentage for when I computed the for the 1 microsecond is much lesser, and electrical losses and input power are closer, much closer to the measured results. But the 10 microseconds is also giving some good results, and which are not as accurate as 1 micro, but the time was reduced to in the next slide I will show you the time which was reduced. And this is taken from my publication, like which was last year publication, and it is in conference ICEPDS. So now if I talk about the computational time, so to check the time consumed by different time step, transient computation is performed with the time step length is 1 second, and mesh nodes are 1,20,000, and 25 cores are used for all the simulations. The relationship between the computational time and time step is not linear as it was in previous slide also. So for the 1 microsecond, the time was almost around 200 hours. So that and when we used the 10 microsecond, the time was reduced to 40 hours, and when the computation was 200 microseconds, the time was reduced to even close to 10 hours. But we find that the accuracy of the results was closer to 1 microsecond at 10 microsecond. So number of hours was reduced to 400%. Number of hours was reduced, and but the results, they were also acceptable. And this is also from my conference paper. And the next slide is about PWM induces losses rise in 5 kilowatt induction machine. Actually, the motor losses with PWM supply at higher are higher than the sinusoidal supply for because of distorted currents. So in PWM supply, harmonics are more in the current, so losses are increased obviously, and there is need to study those this PWM supply in the FEA also to check the behavior. So in PWM supply, the machine experience higher temperatures and reduction in which will reduce the installation time. So typically the electrical machine losses decreases as the switching frequency, but in our case, like we study the machine at different switching frequency in this research. So for that, like we analyze that we analyze that by increasing the switching frequency, the losses also increased. But in the literature, literature and practical point of view, actually it should decrease. But our measurement setup, it showed that with increase in switching frequency, the losses increased. So we want to examine it in FEM also, that is it true in FEM, or is it some fault from the machine, or something. So we recorded that data at 4 kilohertz, 8 kilohertz, 12 kilohertz, and 16 kilohertz. And as I told in previous slide, that I used to downsample this data to 10 microsecond and then feed to the Elmer FEA. And the things we observed in Elmer FEA and commercial FEM also, but commercial FEM data is not here, but I am just discussing the Elmer FEA. And we find that the losses in the Elmer FEM, they showed some trend which is opposite to the Maillard data. So Maillard data, as I told earlier, that it showed that with increase in switching frequency, the losses are increased. But in FEM, if we compare the 16 kilohertz, the losses at 16 kilohertz are 365. It is meant the losses at FEA we observed are 330, round about 330. So there is quite much difference, and the trend is also opposite. So we are also trying to dig out that what could be the reason that the FEA results are opposite to the Maillard results. So by that end, we think that the most of FEAs, they are not able to model the high frequency phenomena, like as seen in the laboratory experiment. And therefore the Maillard results can be only verified with the temperature rise in machine, like some kind of heat simulations in the temperature simulations, thermo simulations. They needed to exactly see what is going on during the simulation. So by that we can actually see. So we have analyzed the flux densities behavior in the air gap and at higher frequencies, and the current FFT also at higher frequency. But we analyzed that at higher frequency it is not showing anything. But on contrary, the measurement results, they are showing something. It can be either due to that our electrical machine, it has some old electrical sheets, or some insulation is not proper, or it can be the on the other contrary, like to this, like it could be the FEM cannot model. So what we think is FEM is having some problem, and but we will dig out further in future. So in future our aim is to further dig out this flux densities, iron losses as a function of switching frequencies, which was in considering 3D model, or efficient 2.5D model. And the next is like we want to speed up our simulations, and we are also in contact with CSE to speed up our simulation. Like we want to compute 1 microsecond results, because the results I showed you earlier, it is using 10 microseconds. So we want to have the 1 microsecond fast computation to get the exact picture. And then the rotating machine heat transfer problem that involve FEM for rotor and stator, and CFD PDE for air gap case ambient thermal interfaces will be studied in future. And for that, like Elmer is still in development, so we are trying to make something like heat transfer analysis in the machines. And our colleague Dr. Chong D, which was my colleague, and he was working with me also. So he is right now in China. He is also working on high speed solid rotor induction machine, and to compute to see the phenomena of Elmer. So quite much work is done in our lab, and we are also doing some practical things and we are trying to take something like which is good for Elmer, and we can also switch to Elmer, and in proficient way. So things are doing. We are carrying the things, and let's see in future. I hope that the commercial FEA will be replaced by open source FEM. So up till now, what I realized that Elmer is quite much efficient, and it can be used very efficiently for the electromagnetics and machine solving the 2D machine problems, and 3D machine problems, and 2.5D problems. So it is giving some good results. So and thanks all for listening. So hope. If you have any question, I can happy to answer.
Okay, so thank you, Minhaj, for such an informative presentation. It was really, really nice. So now, if you have any questions, there's the Q&A tab on the screen. So if you have any questions, just submit them. I will read them for you, Minhaj, if you don't mind.
I will answer it. Like somebody has asked that have you uploaded any example of PWM supply voltage for the motor loss calculation in Git? In Git, if not, could you tell me where we can see the example? Actually, I have not yet uploaded, and actually I am working on it. So if you want, you can contact me. I will be happy to help you, or you can contact CSC administrator. And actually, there are some examples available regarding PWM supply. But if you have any question, you can ask me in person also. Yeah. Yeah. Hello. Hello.
Any other questions?
Right now, I cannot see any other question in QA bar.
So there's a question here. It says, what linear solver do you use?
What linear solver I use for which thing? Actually, for 2D simulations, we used Elmer software solvers like Magneto 2D dynamic solvers for the calculations, and for the loss calculation we use in the post processing we use the as I told in the slides also that we use Bertozzi model. So these solvers they are mentioned in the Elmer solver also, and you can find a lot of examples about these solvers here in the Elmer discussion form also. Yeah, if you people have anything to chip in, so you can also guide them if there is something else.
Okay, here we have another question that says, is there a difference between calculating torques with torque groups and calculating magnetic torque in the component section?
Actually, I don't think so. There is any difference. The only difference which I could see is that it is totally dependent on the mesh size and the time step which you are using. Otherwise, they are almost there is no difference. So I could not find anything like this.
Here's a very interesting question. In the commercial software, you used GPUs, because you talked about something about NVIDIA.
Actually, the commercial software is it is run on our system. Like so, the NVIDIA is used in our personal computers. So So it is not about testing, I think, GPUs. And my supervisor actually, he done this commercial simulations. So commercial simulations, as far as I know, that he has used these things like which I mentioned in the slides. There is one more question.
Okay, I'll read out loud for you. So here it says, in 3D model, are you taking into account eddy current losses? Do you have some scripts for calculating flux linkage that
Actually,
you could share?
I am still building the 3D model, and the 3D model is there, but in my research only 2D and 2.5D is based. So it is possible to calculate the eddy current losses in 3D also, and the flux linkage it can be seen also. So everything is there. So if this guy want to ask something about 3D model and calculating the how the eddy currents are calculated, because its scripts are different from the 2D and 2.5D. So it is using some Whitney solvers to calculate the things and some other solvers to calculate this. So this guy can also contact me, and I will happy to answer this in private.
Okay, I guess that was our last question. Okay, I guess it was. So thank you, Minhaj, for such an informative webinar once again.
Thank you.
I really enjoyed seeing the benefits of using parallel computations and how much you can speed up such heavy models. So
actually, I just want, sorry to interrupt you. I want to say that we, in collaboration with the CSC, are also looking to use our own system. Like in this series, like I have used CSC supercomputers. So I want to use my computer, and we want to make it more efficient, like using our own computer. Like, so for these small simulations, like for 2-3 hour simulation, 5 hour simulations, you should have some efficient code. So you don't need to access the CSC servers to use the parallelization and supercomputing to solve the issues. So we are also doing something like to manage the things and speeding up the simulation by using our own system codes. So we are actually working on it, and hopefully there will be something after some time. Yeah.
Oh, that's great to hear. All right, so let's wrapping up. So here in this slide, basically what I'm showing you is where you can find further information about this particular webinar. So everything is uploaded onto the nicfunit.fi link, and the webinars are eventually uploaded. I think, I don't know if it's today or within this week, in our YouTube channel. We have a YouTube channel. And if you have any technical questions, I recommend using the Elmer forum, which is pretty active. And every now and then, me and my colleagues chime in and try to help the users. And if you have some feedback or anything you want to tell us about with respect to Elmer, you can email us directly to Elmer ADM. And well, remember, this is just one webinar out of a series of webinars. So if you're interested, you can attend the next webinar next week. So for instance, next week we'll be presenting, well, about how to use Elmer interface with Python. No, I'm sorry. Well, no, it's sorry, I misread. It's the one about industrial applications in microwave modeling with Elmer. So, and remember, all the other ones will be uploaded on our YouTube channel. So don't hesitate if you want more information or learn about other topics that maybe weren't touched upon today. You can definitely just sign up. They're for free. And Not only that, we have all these links. So if you're interested in knowing more about Elmer or how to install it, you can always go to our homepage. As I mentioned before, the forum is always active. You can ask questions. There will be people working maybe on similar topics, so you can create a network within the network, the Elmer network. We have not only the source code in our repository under GitHub, but we also have multiple tutorials and models that you can use as templates just to build up and feel more comfortable with modeling with Elmer. As I mentioned before as well, we have our YouTube channel, Elmer FEM. We have nice animations, potential applications. We also have instructional videos about how to install Elmer, how to run it in parallel. I think that's very important. More documentation on Funit and the Discord. We're also very active there. There are multiple channels there. You can interact with other users. And for further information, just send us an email to elmeradm@csc.fi. I really hope you enjoyed the webinar today, and have a nice day.
Yes, and an official thank you to the speakers, and on behalf of CSC and everyone else, have a nice continuation of the day. And this webinar ends now in about a minute.